In this video, we're going to show you how to solve this second order circuit here. Now the first thing I would do is try to write out my differential equation. In order to do that, we need to figure out if it's going to be RLC series or RLC parallel once the switch opens. So if we have the switch open and we redraw the circuit here. We have this inductor. We have this resistor. The middle part of the circuit is going to open up and go away. It's not going to be connected anymore, so we can ignore it. Then we have our capacitor, that's 0.8 farads. And then we've got 24 volts here. And we're trying to find the voltage across the capacitor. So we see that this is going to be an RLC series circuit here. And we know from the video about RLC series is that we can have VC double prime, whatever variable we're looking for, plus R over L VC prime, plus 1 over LC VC equals 0. This is our standard homogeneous part of the differential equation for an RLC series. So in this case, we have an R value of 1 and an L of 0.25. 1 over 0.25 is going to be 4. And then L times C is 0.25 times 0.8 is 0.2. Divide by that, you're going to get 5 VC. So then my auxiliary equation would be S squared plus 4S plus 5 equals 0. Can't factor that nicely, so we go to quadratic formula. B squared is 16 minus 20 over 2a. And we're going to get as negative 2 plus or minus, let's see, square root of 4 is 2i, plus or minus 1i here. So that means our default equation for the homogeneous part would be k1 e to the negative 2t cosine 1t plus k2 e to the negative 2t sine t plus some constant, which we'll have to figure that out. It's going to be the value at infinity. So if I now look at the circuit as we go to infinity, well, in steady state, an inductor becomes a short. We have a resistor, the same thing. The capacitor becomes an open. We have our same source here. So I need to know what is the voltage across the capacitor in this infinity case. Well, in an open circuit, there's no current flowing. So no current flowing means there's no voltage drop across the resistor. Inductors are shorts, there's no voltage drop there. So the entire 24 volts is going to have to drop over the capacitor. So that means the VC of infinity is 24 volts, which means my C constant is 24. So I have that value there. I know my final value in this case. Now the next thing I need to worry about is the initial conditions, and I need 2 of them in order to get the answer. So now we're going to have to look at what happens on our switch. So we're going to look at t equals 0 minus. So right before the switch happens, it's in steady state. So inductor over here is a short. We have our resistor. The switch is still closed here. We have another resistor. We have a 12 volt source down here. We do have an opening on this capacitor with a 20 volt source here. Okay, so because of the open, the current that's going through the circuit is not going to go on the right side at all. So really, we just have current flowing around this left loop here. And we can just do 12 volts over 6 ohms. It's going to be a 2 amps here, which means there's a 10 volt drop across the 5 ohm resistor, which means at this point, we are going to be at 2 volts. And that means this one's 24 volts from the source. So that means my VC of 0 minus, which because it's a voltage across a capacitor, is also my VC of 0 plus. is going to be this difference between those two. That's 22 volts. Now I can also say that my current through my inductor here, my IL of 0 minus, since my inductor is really right here on the left side, same as IL of 0 plus, is going to be 2 amps. So with this here, since we are actually looking for the VC, we can plug it in and we'll be able to find one of the K values. So if I plug in VC of 0 into my formula up here, the cosine part would stick around, be K1, e to 0 is 1, cosine 0 is 1. My sine part's going to go away because sine of 0 is 0 plus 24. And based on this, it's supposed to equal 22. So that means my K1 is at negative 2. So we have that part done. Now we need to find our K2, and for that we need to know our derivative. So first off, what happens if you take the derivative of VC? Well, if you take that and then you multiply it by the capacitance value, that would be the current through the capacitor. Okay, so what do we know our current through a capacitor? Well, as the switch opens up, t equals 0 plus, we have our inductor, we have our resistor, we have the middle part's gone, so we can ignore it. And then we have our capacitor over here. Well, the thing is we knew that before the switch happened, there was 2 amps going through the inductor. And because current can't change instantaneously through an inductor, there has to still be 2 amps right after the switch happens, which means the current through the capacitor here is also going to be 2 amps at 0. When you plug in 0, you get 2 amps. So that means if I take the derivative of my voltage, multiply it by C, and plug in 0, we're going to get 2 amps. So once again, I need to take this formula I got and take the derivative. I do know my K1 is negative 2 at least. So I'd have negative 2, and then the derivative of e to the negative 2t cosine t is going to be negative 2 e to the negative 2t cosine t plus e to the negative 2t times negative sine t plus K2 times the derivative of the second part. That'd be negative 2 e to the negative 2t sine t plus e to the negative 2t cosine t. The derivative of the 24 is 0. And then if you take this whole thing, you plug in t equal to 0, and you multiply it by the capacitance, 0.25. It's supposed to equal 2 amps. So let's see what happens when you plug in 0 everywhere. Well, in the first term, we got a cosine and e are both going to go to 1, so it's going to be times negative 2 is positive 4. Second one with the sine is going to go to 0 because sine of 0 is 0. Third term, again, sine of 0 is 0. Fourth term is going to be just plus K2 equals 2. And so by solving this, we're going to get K2 is 1 here, which means my final answer then, VC of t, K1 was negative 2 e to the negative 2t cosine t plus 1 e to the negative 2t sine t plus 24. So you can see writing out the differential equation is actually the easy part on this problem. You solve for your S values, you get your standard solution. Even solving for the plus C part at infinity, that doesn't take that much time. It's always solving for the K1 and K2 that's going to be the most effort. And that's where you have to look at the switch, see what happens, know your steady state results, and put all this together along with the derivative somewhere to get the answer you're looking for.